Hello there and welcome back to the Science Sleepy Minds. You're floating in absolute darkness. Not the cozy darkness of your bedroom right now, but the kind of void that stretches across 10 billion light years of empty space. And then, cutting through that nothingness like a cosmic searchlight, you spot it. A single point of light so impossibly bright that it outshines a trillion stars combined. That's TON 618. And honestly, you probably won't survive even thinking about getting close to it. The radiation alone would disassemble your atoms long before gravity got a chance to stretch you into cosmic spaghetti. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, drop a comment below telling me where you're watching from and what time it is in your corner of the world. I love seeing the Global Insomnia Club check in. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. The story of TON 618 begins not with a bang, but with a bureaucratic catalogue entry. It's 1957, and astronomers are compiling the Tonantzintla Observatory Catalogue in Mexico, a star survey that sounds more like a sneeze than a scientific project. Some patient researcher is photographing chunks of sky, numbering objects, and one particular speck gets labelled number 618. Nothing special, just another faint smudge on a photographic plate. Fast forward to the 1970s, radio astronomers start noticing that this unremarkable dot is screaming in frequencies human eyes can't see. It's not a star, it's not a normal galaxy, it's something else entirely. A quasar, back when quasars were still the new weird kids on the cosmic block. You scan it with better instruments, and the numbers start coming back wrong. The brightness readings seem like equipment errors. The distance calculations make you double-check your math 3 times. By the time we reach the early 2000s, with space telescopes and adaptive optic systems that can peer through Earth's atmospheric blur, the truth becomes unavoidable. TON 618 isn't just big. It's grotesquely, absurdly, rule-breakingly massive. We're talking about a black hole with a mass of 66 billion suns. Not million, billion. With a B that stands for, you've got to be kidding me. Here's where it gets deliciously weird. The original discoverers had no idea what they'd found. They were just doing their job, cataloguing the sky like cosmic accountants. TON 618 sat in that database for decades like a ticking time bomb of scientific disruption, waiting for technology to catch up. It's the astronomical equivalent of buying a painting at a yard sale and discovering 50 years later that it's a lost Rembrandt. Historians still argue whether the early quasar researchers suspected how monstrous these objects could become. The initial model suggested supermassive black holes might top out around a few million solar masses, maybe 10 million if you were being wildly optimistic. TON 618 laughs at those predictions. It's roughly 1,500 times more massive than Sagittarius A star, the supermassive black hole at the centre of our Milky Way. Imagine thinking you've figured out the upper limit of something, and then the universe casually presents an example that exceeds your maximum by 3 orders of magnitude. What makes this discovery even more mind-bending is that TON 618 isn't just massive, it's ancient. The light you observe from it today left that region of space 10.8 billion years ago, when the universe itself was barely a toddler in cosmic terms. You're seeing this beast as it was less than 3 billion years after the Big Bang, which raises an uncomfortable question that keeps cosmologists awake at night. How did anything get that stupidly large, that stupidly fast? Black holes are supposed to grow gradually, snacking on nearby stars and gas clouds over billions of years. But TON 618 apparently went through the cosmic equivalent of an all-you-can-eat buffet in the universe's early epochs. It's like finding a 40-year-old oak tree in a forest that's only been standing for 50 years. The math doesn't quite add up, and that's what makes it fascinating. The modern observation campaigns involve coordinating telescopes across multiple continents, stitching together data from radio arrays, optical surveys, and X-ray satellites. TON 618 doesn't make this easy. It's obscenely far away, and you're essentially trying to study something the size of our solar system from a distance that light takes 10.8 billion years to cross. It's like trying to examine a grain of sand on a beach in Australia while you're standing in Alaska, except the sand is also invisible and surrounded by the brightest floodlights in existence. Here's a quirky tidbit. The energy output from TON 618 is so extreme that if you somehow placed it at the centre of our galaxy, instead of Sagittarius A star, the radiation would probably sterilize every planet within thousands of light years. Earth wouldn't just be uninhabitable, it would be vaporized down to its constituent atoms. Sweet dreams, right? You settle deeper into your pillow, trying to wrap your mind around those numbers, and the sheer indifference of TON 618 is oddly comforting. It's been blazing away for eons, completely unaware of humans, civilizations, or the tiny creatures who finally spotted it in a telescope and gave it a catalogue number. It just exists, crushing space-time around itself, the universe's heavyweight champion that nobody asked for. Now that you know TON 618 exists, let's talk about what 66 billion solar masses actually means, because your brain isn't equipped to process numbers that large without help. Picture our Sun first. It's already incomprehensibly massive compared to Earth. You could fit about 1.3 million Earths inside the Sun's volume. The Sun contains 99.86% of all the mass in our solar system. Everything else, Jupiter, Saturn, all the planets, moons, asteroids, comets, and that weird dust floating around, accounts for barely a rounding error. This Sun is the gravitational tyrant of our neighbourhood, and it weighs roughly 2 × 10 to the power of 30 kilograms. That's a 2 followed by 30 zeros. Already your brain is checking out. Now multiply that mass by 66 billion. Go ahead, try. Your calculator might actually give up. TON 618 contains the equivalent of 66 billion stars like our Sun, except instead of being spread across a galaxy, all that mass is compressed into a region smaller than our solar system. It's not even matter anymore in any conventional sense. It's a gravitational singularity surrounded by an event horizon, the point of no return where physics as we understand it politely excuses itself from the conversation. Here's a comparison that might help, though help is generous. The entire Milky Way galaxy contains somewhere between 100 to 400 billion stars. Sounds like a lot, right? But most of those stars are wimpy red dwarfs with a fraction of the Sun's mass. If you add up all the stellar mass in the Milky Way, you get roughly 60 billion solar masses. TON 618, a single object, has more mass than all the stars in our galaxy combined. It's one black hole wearing our entire galactic population as a light snack. Let's get even weirder. Scientists estimate the Milky Way's total mass, including dark matter, at about 1.5 trillion solar masses. Sounds like TON 618 is small potatoes now, right? Except most of that mass is dark matter spread across a halo hundreds of thousands of light years wide. The actual visible, matter you can touch stuff is that 60 billion solar mass figure. TON 618 beats it while occupying a space you could, theoretically if you had a really fast spaceship and a death wish, cross in a few light hours. Historians still argue whether black holes have a theoretical upper limit. Some models suggest that beyond a certain mass, black holes become so efficient at blasting away nearby matter with radiation that they can't eat fast enough to grow larger. It's called the Eddington limit, and it's basically the universe's way of saying, okay, that's enough. But TON 618 seems to have ignored that suggestion entirely, possibly by growing during an era when the universe was denser and the buffet was better stocked. You're probably wondering what this looks like. Spoiler, you can't see the black hole itself. Black holes are black because nothing, not even light, escapes once it crosses the event horizon. What you actually observe is everything around TON 618 losing its mind. The accretion disk, we'll get to that properly in a later section, glows so intensely that TON 618 qualifies as one of the brightest objects in the known universe. It's the ultimate irony. The darkest thing in existence surrounded by the brightest light show. Here's your quirky fact for this section. If you converted TON 618's mass directly to energy using Einstein's E equals mc squared, you'd get a number so large it would power every star in the observable universe for trillions of years. Not that you can extract that energy, it's locked behind an event horizon, but it's a fun thought experiment for 2 AM. The mass also does something disturbing to space-time itself. Imagine space-time as a rubber sheet. The old trampoline analogy. A marble creates a small dip. A bowling ball makes a deeper one. TON 618 doesn't just dip the sheet, it punctures it, creating a well so steep that the walls are essentially vertical. Anything wandering too close doesn't roll in gradually, it falls straight down, accelerating to a significant fraction of a light speed before the event horizon swallows it whole, and that mass is increasing. Right now, in the present tense of TON 618's existence, remembering that we're seeing it as it was 10.8 billion years ago, it's actively feeding. Matter spirals inward, adding to the total mass with every passing moment. If we could somehow watch TON 618 and fast forward over 1 million years, we'd see it visibly fattening, like a cosmic python digesting a very large meal. Astronomers calculate that at its peak, feeding rate, TON 618, might be consuming material equivalent to several hundred Earths per minute. Let that sink in while you're sinking into your mattress. In the time it takes you to brew a cup of tea, TON 618 has eaten a small solar system's worth of matter. The truly disturbing part. TON 618 isn't even the theoretical maximum. Physicists have run the numbers on what they call ultramassive black holes, pushing into the 100 billion solar mass range. We haven't found one yet, but the math says they could exist. TON 618 might just be the current record holder, waiting for us to discover something even more obscene lurking in a distant corner of space-time. You shift your position, pulling the blanket higher, and somewhere in the back of your mind, that number keeps echoing. 66 billion suns. It's the kind of number that should mean something profound, but it's so far beyond human experience that it just becomes a pleasant abstraction, a bedtime story about impossibly large things happening impossibly far away. Which honestly is exactly what you need right now. So TON 618 is a quasar, and if you've been half asleep already, you might be wondering what that word even means. Let's fix that, because quasars are basically the universe showing off. The term quasar is short for quasi-stellar radio source, which is scientists speak for, we thought it was a star, but it's definitely not a star, and we're not entirely sure what's happening. When astronomers first spotted these objects in the 1960s, they looked like stars in optical telescopes, single points of light, not fuzzy like galaxies. But they were absurdly bright and emitting powerful radio waves, which normal stars don't do. It was cosmology's version of opening what you thought was a can of soup and finding live octopuses inside. Here's what's actually happening. A quasar is what you get when a supermassive black hole in the centre of a galaxy goes through its teenage growth spurt and starts eating everything in sight. As matter spirals into the black hole, it forms an accretion disk. Imagine a whirlpool made of superheated gas, dust and shredded stars. Friction within that disk heats the material to millions of degrees, and at those temperatures matter doesn't just glow. It screams across the electromagnetic spectrum, pumping out radio waves, visible light, ultraviolet, X-rays, the works. TON 618 is a quasar cranked up to 11. It's so luminous that it outshines its entire host galaxy by a factor of hundreds. If you could somehow view the galaxy from outside, you wouldn't see the billions of normal stars. You'd just see the blinding pinpoint of the quasar in the centre, like trying to spot a candle next to a searchlight. The galaxy is there, quietly minding its own business, but the quasar is the cosmic equivalent of that one person at a party who won't stop talking. What makes quasars fascinating is that they're time capsules. Because light takes so long to reach us from these distances, every quasar we observe is a snapshot of the ancient universe. TON 618's light left home 10.8 billion years ago, back when the universe was less than a quarter of its current age. You're seeing this object as it existed before Earth formed, before the sun ignited, before our entire solar system was even a twinkle in a nebula's eye. Historians still argue whether quasars represent a specific phase in galaxy evolution, or if they're just galaxies that happen to have well-fed black holes at the moment we're looking. The leading theory is that quasars were more common in the early universe because galaxies were closer together and mergers were frequent. When galaxies collide, gas gets funneled toward the central black hole, triggering a feeding frenzy. TON 618 might be the aftermath of a massive galactic pileup, several galaxies merging and dumping all their gas into one monstrous central sink. Here's the quirky bit. Quasars are so bright that they can actually push material away through sheer radiation pressure. Photons, particles of light, carry momentum. When you're pumping out as much light as TON 618, those photons collectively hit surrounding gas clouds like a stellar wind, blowing material outward at thousands of kilometers per second. It's the universe's most violent self-regulating mechanism. The quasar eats, gets brighter, then blows away its own food supply. Efficient? Not really. Spectacular? Absolutely. From a practical standpoint, quasars like TON 618 serve as cosmic lighthouses. Because they're so luminous, we can detect them across vast distances, using them to map the structure of the early universe. Astronomers measure the light spectrum, look for absorption lines caused by intervening gas clouds, and piece together the distribution of matter between here and there. TON 618 isn't just an object. It's a probe we can use to study everything in its light path. The energy output is almost offensive in scale. TON 618 radiates about 4 times 10 to the power of 40 watts. For context, the sun outputs about 3.8 times 10 to the power of 26 watts. So TON 618 is roughly 100 trillion times more luminous than our sun. If you replace the sun with TON 618, please don't. Earth's surface would receive so much energy that the entire planet would vaporize in under a second. The oceans would flash into plasma. The atmosphere would be stripped away at near light speed. Even the iron core would probably get nervous. And that energy isn't just heat and light. Quasars emit across the spectrum, including hard X-rays and gamma rays. If you were somehow orbiting TON 618 at a safe distance, a concept that barely applies here, you'd need shielding thick enough to stop a nuclear bomb's worth of radiation every second. Spacesuits wouldn't cut it. You'd need a bunker made of lead and crossed fingers. You roll over, adjusting the pillow, and think about that pinpoint of light blazing across the universe. It's been doing this for billions of years, possibly longer than the light has taken to reach us. Right now, in TON 618's present, it might have calmed down, run out of nearby food, and settled into a quiet retirement. Or maybe it merged with another black hole and became even more monstrous. You'll never know, because the light showing you that future won't arrive for another 10.8 billion years, long after the sun has died and Earth is a cinder. Quasars are proof that the universe doesn't care about our sense of scale or decency. They exist because the laws of physics permit them, and TON 618 is the poster child for cosmic excess. A black hole so massive and so hungry that it turned an entire galaxy into its personal spotlight. Let's talk about distance, because saying TON 618 is far away is like calling the Pacific Ocean damp. It sits roughly 10.8 billion light-years from Earth, and unpacking what that means will help you understand why studying it is such a magnificent headache. First, the light-year itself. It's not a unit of time, despite the name tricking your sleepy brain. A light-year is the distance light travels in 1 year through the vacuum of space. Light moves at 299,792 kilometers per second. Fast enough to circle Earth's equator about 7.5 times in a single second. Over a year, that adds up to roughly 9.46 trillion kilometers, or about 5.88 trillion miles if you prefer your existential dread in imperial units. Now multiply that by 10.8 billion. The number becomes so large it's essentially meaningless to human intuition. Ton 618 is about 102 sextillion kilometers away. That's a 1 with 23 zeros after it. Your brain has no framework for this. You can't drive it, walk it, or even meaningfully visualize it. It's just far. Very, very far. Here's a thought experiment to make it slightly less abstract. If you could somehow travel at the speed of a light, which you can't, because mass and physics conspire against you, it would still take 10.8 billion years to reach Ton 618. The entire recorded history of human civilization spans maybe 10,000 years, generously. You'd need to repeat all of human history, from the first agricultural settlements to smartphones, over 1 million times consecutively just to cover that distance, and that's at light speed. The Voyager 1 spacecraft, humanity's most distant emissary, is currently zipping away from the Sun at about 17 kilometers per second. It's been flying since 1977 and has covered roughly 23 billion kilometers, a distance that sounds impressive until you realize it's taken over 4 decades to get there, and it's barely left the solar system's front porch. At Voyager 1 speed, reaching Ton 618 would take approximately 190 quadrillion years. The universe itself is only 13.8 billion years old. You'd need the universe to live, die, and be reborn several trillion times over. Pack snacks. But here's where it gets cosmologically weird. That 10.8 billion light-years figure is the light travel distance, how long the light has been flying to get here. Due to the expansion of the universe, Ton 618's actual present-day distance is much larger. Space itself has been stretching while that light was in transit, so the object is now roughly 18 billion light-years away in moving coordinates. It's like mailing a letter from a city, and by the time the letter arrives, the city has drifted to another continent. Relativity and cosmic expansion make distance a surprisingly slippery concept. Historians still argue whether distant objects like TON 618 should be described by light travel time, co-moving distance, or proper distance. Each measures something slightly different, and cosmologists love a good argument about definitions. For practical purposes, we stick with light travel time because it tells you when you're seeing the object from 10.8 billion years ago. Here's your quirky detail. The light you observe from Ton 618 today began its journey when the universe was about 3 billion years old. Earth didn't exist yet. The Sun didn't exist. The Milky Way was still a young galaxy figuring out its structure. Early life on Earth, single-celled organisms floating in primordial oceans, wouldn't appear for another 6 billion years. That photon has been flying through space longer than our planet has existed, crossing voids between galaxy clusters, threading through intergalactic gas until it finally smacks into a telescope mirror and gets counted by some astronomer's detector. Distance also affects how we observe TON 618. The expansion of the universe stretches light waves as they travel, shifting them toward the red end of the spectrum, a phenomenon called redshift. Ton 618 has a redshift value of about 2.219, meaning its light has been stretched to roughly 3.2 times its original wavelength. Ultraviolet light emitted by the quasar arrives here as visible or even infrared light. Astronomers have to correct for this shift to figure out what Ton 618 actually looks like in its own reference frame. And because of that distance, TON 618 appears incredibly faint despite being one of the most luminous objects in the universe. The light spreads out over the surface of an ever-expanding sphere, and by the time it reaches Earth, it's diluted to almost nothing. Ton 618's apparent magnitude, how bright it looks from here, is about 15.9, which is roughly 4,000 times fainter than the dimmest star you can see with your naked eye. You need a decent-sized telescope just to spot it at all. This creates a strange paradox. Ton 618 is simultaneously one of the brightest and faintest objects we know. Intrinsically, it's a cosmic searchlight. Observationally, it's a barely there smudge on a detector. Distance is the ultimate humbler. You let your eyes drift shut, thinking about photons travelling for eons across the universe, indifferent to the stars and galaxies they pass, just moving forward at the only speed they know. By the time they arrive here, the universe that emitted them is long gone, transformed beyond recognition. You're seeing a ghost, a snapshot of something that might not even exist anymore in any recognisable form. It's the ultimate cosmic time capsule delivered via light. Now let's talk about the accretion disk, because this is where TON 618 goes from terrifyingly massive to actively nightmare-inducing. The accretion disk is the swirling death trap of matter that feeds the black hole, and it's one of the most violent environments in the known universe. Picture a whirlpool, but instead of water, it's gas, dust, plasma, and the shredded remains of stars that got too close. This material doesn't fall straight into the black hole. Angular momentum won't allow it. Instead, it spirals inward, forming a rotating disk that extends outward for potentially hundreds of billions of kilometers. The inner regions of this disk are moving at a significant fraction of light speed, whipping around the black hole in a screaming vortex of superheated matter. Friction is the key villain here, as material in the disk rubs against neighbouring regions, inner layers moving faster than outer ones. Friction generates heat. Not campfire heat, not even surface of the sun heat. We're talking tens of millions of degrees Kelvin in the outer disk, ramping up to hundreds of millions or even billions of degrees closer to the event horizon. At those temperatures, atoms are ripped apart into plasma, and the disk glows like a cosmic forge. This is why quasars are so bright. The accretion disk around TON 618 converts gravitational potential energy into radiation with terrifying efficiency. Up to 40% of the infalling mass gets transformed into light and heat, compared to nuclear fusion's measly 0.7% efficiency. Black holes are the universe's best engines, and TON 618 is running at full throttle. Historians still argue whether accretion disks are smooth, uniform structures, or chaotic, turbulent messes. The current consensus leans toward chaos. Magnetic fields thread through the plasma, creating instabilities and turbulent eddies. Matter doesn't flow smoothly inward. It clumps, swirls, and occasionally gets flung outward in violent bursts. The disk probably flickers and varies in brightness over timescales ranging from hours to years, though from 10.8 billion light-years away, we can't catch those rapid changes. Here's a quirky detail. The inner edge of the accretion disk doesn't actually touch the event horizon. There's a gap, a region called the Innermost Stable Circular Orbit, or ISCO. Inside this radius, space-time is so warped that stable orbits become impossible. Matter reaching the ISCO either plunges directly into the black hole or gets ejected outward in a final, desperate escape attempt. For a non-rotating black hole, the ISCO sits at about 3 times the Schwarzschild radius, the size of the event horizon. For a rapidly spinning black hole, it can be much closer, almost kissing the event horizon itself. We don't know TON 618's spin rate yet, but given its mass and feeding rate, it's likely rotating fast. The disk also emits across multiple wavelengths simultaneously. The hottest inner regions blast out X-rays and ultraviolet light. The cooler outer zones glow in visible and infrared. Radio waves emerge from magnetic interactions and particle acceleration. Observing TON 618 requires stitching together data from radio telescopes, optical surveys, X-ray satellites, and infrared observatories, each catching a different piece of the story, like blind people describing an elephant, except the elephant is a physics-defying death disk, and the mass flow rate is staggering. Estimates suggest TON 618's accretion disk is funneling somewhere between tens and hundreds of solar masses per year into the black hole. For context, our sun's entire mass is consumed in a year or less. Imagine an entire star, its core, its corona, everything, getting shredded and devoured annually and that's TON 618's normal Tuesday. The disk is also thick, geometrically speaking. In less extreme systems, accretion disks are razor thin like cosmic vinyl records. But with TON 618's feeding rate, radiation pressure puffs the disk outward, making it fatter and more bloated. Parts of the disk might even rise above and below the main plane, creating a warped, three-dimensional structure that defies your mental image of a neat, flat spiral. Let's talk about what happens to material in the disk, because it's not a peaceful journey. As gas spirals inward, it heats up, ionizes, and starts emitting light. But it's also getting compressed, stretched by tidal forces, and bombarded by radiation from the inner disk. Atoms lose their electrons, molecules disintegrate. Anything resembling solid matter is vaporized within seconds. If you somehow dropped a chunk of iron into the outer accretion disk, it would melt, boil, ionize, and turn into plasma faster than you could blink. And the magnetic fields, oh, the magnetic fields. The disk's plasma conducts electricity, and as it spirals, it drags magnetic field lines into twisted, tangled knots. These fields can snap and reconnect in violent bursts, accelerating particles to near-light speeds and firing them outward in narrow jets. We'll get to those jets properly later, but for now, just know that the accretion disk isn't just feeding the black hole. It's also a particle accelerator, a fusion reactor, and a cosmic dynamo all wrapped into one nightmarish package. You pull the blanket tighter, imagining that glowing disk stretching across a region larger than our solar system, spinning faster than anything you've ever seen, hot enough to vaporize planets, bright enough to outshine galaxies, and at the center, patient and inexorable, TON 618 waits, pulling everything inward, one atom at a time, adding to its already incomprehensible mass. It's been doing this for billions of years, and it's not stopping anytime soon. Let's measure the event horizon, because this is where numbers stop being abstract and start feeling like cosmic horror. The event horizon is the point of no return, the boundary where escape velocity equals the speed of light. Cross it, and you're not coming back. Not with rockets, not with magic, not with wishful thinking. Physics says no, and physics doesn't negotiate. For a non-rotating black hole, the event horizon radius is given by the Schwarzschild radius formula. R equals 2gm over c squared, where g is the gravitational constant, m is mass, and c is the speed of light. Plug in TON 618's 66 billion solar masses, and you get an event horizon radius of roughly 195 billion kilometers, or about 1,300 astronomical units. An astronomical unit, for reference, is the average distance between Earth and the Sun, about 150 million kilometers. So TON 618's event horizon is 1,300 times that distance. Let's put that in solar system terms because your brain needs landmarks. Earth orbits the Sun at 1 astronomical unit. Mars is at 1.5 astronomical units. Jupiter is around 5 astronomical units. Saturn sits at about 10 astronomical units. Neptune, the outermost major planet, orbits at roughly 30 astronomical units. The Kuiper Belt, home to Pluto and other icy bodies, extends to maybe 50 astronomical units. The event horizon of TON 618 would swallow all of that and keep going. In fact, you could fit our entire solar system, Sun, planets, asteroid belt, Kuiper Belt, everything we consider local space, inside TON 618's event horizon multiple times over. The heliopause, the boundary where the Sun's solar wind peters out and interstellar space begins, sits at about 120 astronomical units. TON 618's event horizon is nearly 11 times wider. It's not a black hole, it's a black continent. Historians still argue whether spinning black holes, Kerr black holes, have larger or more complex event horizons. The answer is, it depends. A rapidly spinning black hole can have an ergosphere, a region outside the event horizon where space-time itself is dragged around. Objects in the ergosphere can still escape, but they're forced to rotate with the black hole whether they like it or not. We don't know if TON 618 spins, but given the angular momentum of all the material it's swallowed, it almost certainly does. Here's your quirky fact. If TON 618 were rotating near the maximum theoretical limit, an extremal Kerr black hole, the event horizon would actually shrink slightly, but the ergosphere would extend much farther. The physics gets weird here, allowing for theoretical processes like the Penrose mechanism, where you could extract rotational energy from the black hole. Not that you'd survive the attempt, but it's a neat idea. Now imagine approaching this thing. You're in a spacecraft, coasting through space, and ahead of you is nothing. Just blackness. The event horizon doesn't glow or announce itself. It's not a wall or a membrane, it's just the geometric boundary where light gives up. You wouldn't see it until you were almost on top of it, and by then your fate would already be sealed by the gravitational gradient pulling you inward. The event horizon's size also has implications for what's happening inside, though inside is a misleading term since information can't escape to tell you. General relativity predicts a singularity at the centre, a point of infinite density where the laws of physics break down completely. But that singularity is hidden behind the event horizon, a cosmic censorship that prevents the universe from having to display its mathematical nervous breakdowns. For TON 618, the singularity might not even be a point. Some models suggest it could be a ring-shaped structure if the black hole is spinning. But you'll never know, because measuring it would require crossing the event horizon, and once you do that, your ability to report findings drops to zero. You become information that the universe has deleted. Let's compare this to other black holes for perspective. Sagittarius A star, the supermassive black hole at the centre of the Milky Way, has a mass of about 4.1 million solar masses and an event horizon radius of roughly 12 million kilometres, about 0.08 astronomical units. That's already enormous, but TON 618's event horizon is over 16,000 times larger by radius. If Sagittarius A star is a marble, TON 618 is a beach ball the size of a city. Even among supermassive black holes, TON 618 is an outlier. Most galactic centres host black holes in the million to billion solar mass range, with event horizons measured in millions or tens of millions of kilometres. TON 618 is operating on a scale that feels almost excessive, like the universe experimenting with how large it can make something before the math collapses. And remember, the event horizon itself is just empty space. There's no surface, no structure, no there. It's purely a geometric consequence of mass warping space-time. If you could somehow hover just outside the event horizon, ignoring the radiation, tidal forces and screaming physics, you just see distorted starlight as the curvature bends light paths around you. The black hole itself remains invisible, a void defined only by what it isn't. You shift positions, half asleep, and picture that boundary stretching across space, an invisible sphere larger than your comprehension, marking the edge of a region from which nothing returns. It's less a physical object and more a philosophical statement. Beyond this point, causality itself flows in only one direction. Inward, always inward, until even the concept of you ceases to have meaning. Now let's discuss why TON 618 is so preposterously bright, because this is where the black hole stops being just a gravitational monster and becomes a cosmic floodlight visible across most of the observable universe. We've already established that the accretion disk is hot, millions to billions of degrees, but let's talk about what that heat translates into. Radiation. Lots and lots of radiation. When you heat matter to extreme temperatures, it doesn't just glow faintly like a toaster coil. It emits photons across the entire electromagnetic spectrum, from low-energy radio waves to high-energy gamma rays. The hotter the material, the shorter the wavelength of peak emission. TON 618's inner accretion disk is so hot that it's pumping out X-rays and ultraviolet light like a malfunctioning nuclear reactor. The total luminosity, the amount of energy TON 618 radiates per second, is approximately 4 times 10 to the power of 40 watts. For scale, the Sun's luminosity is about 3.8 times 10 to the power of 26 watts. Ton 618 is roughly 100 trillion times brighter than our Sun. If you wanted to match Ton 618's output, you'd need to gather about 140 trillion Sun-like stars and turn them all on simultaneously. Even then, you'd barely be in the ballpark. This energy comes from gravitational potential energy being converted into radiation as matter falls into the black hole. It's mass energy conversion via Einstein's E equals mc squared, but instead of nuclear reactions, you're using gravity as the engine. As particles spiral inward through the accretion disk, they lose gravitational potential energy, which manifests as heat and light. The efficiency is staggering. Up to 40% of the infalling mass can be converted into radiation. Nuclear fusion, by comparison, converts less than 1% of mass into energy. Black holes are the universe's most efficient power plants, and Ton 618 is running at peak capacity. Historians still argue whether quasars like Ton 618 experience variability in their brightness, whether they flicker over human timescales or remain steady. Observations of closer quasars show variability on timescales from hours to years, suggesting the accretion process is turbulent and chaotic. But Ton 618 is so far away that even if it's flickering wildly in its own time frame, we'd struggle to detect short-term changes. The light gets time-dilated by the universe's expansion, stretching variability patterns into longer observed timescales. Here's the quirky bit. TON 618's radiation output is so intense that it affects its surroundings on galactic scales. The light and particle flux from the quasar can heat and ionize gas clouds thousands of light-years away, suppressing star formation in nearby regions. This is called quasar feedback, and it's one of the mechanisms that regulates galaxy growth. A quasar can literally blow away the raw material needed to make new stars, putting its host galaxy on a starvation diet. TON 618 might have sterilized large swathes of its home galaxy, turning potential star-forming regions into hot, empty voids. The radiation pressure is also strong enough to drive winds, streams of gas blasted outward at thousands of kilometers per second. These winds carry energy and momentum away from the black hole, distributing it across the galaxy and even into intergalactic space. It's a feedback loop. The black hole eats, gets brighter, blows away its food, then has to wait for more material to settle back down before resuming the feast. Ton 618 might go through cycles of feeding and fasting over millions of years. Let's talk photon pressure, because it's one of those concepts that sounds gentle, but is actually terrifying at this scale. Photons carry momentum. When a photon hits something, it imparts a tiny push. Normally this is negligible. Sunlight pushes on your skin, but you don't feel it. But when you have 10 to the power of 40 watts of radiation, the collective push from trillions upon trillions of photons becomes a physical force strong enough to move gas clouds, dust, and even stars if they're light enough. TON 618's radiation pressure is essentially a stellar wind made of light, shoving matter around like a cosmic leaf blower. And here's the disturbing part. If you were somehow near TON 618, say orbiting outside the accretion disk at a safe distance, you'd be bathed in radiation intense enough to vaporize any material object within seconds. Forget spacesuits, forget shielding. You'd need meters-thick lead plating, and even then, the heat would melt it. The X-rays alone would dose you with lethal radiation levels thousands of times over before you could register what was happening. Ton 618 doesn't just kill you with gravity, it cooks you with light. The energy output also makes Ton 618 a cosmological beacon. Because it's so luminous, we can detect it across vast distances, making it a useful reference point for mapping the early universe. Astronomers use quasars like TON 618 to trace the distribution of matter, study the growth of supermassive black holes, and understand how galaxies evolve over cosmic time. It's a natural laboratory for extreme physics, conveniently located 10.8 billion light-years away so it can't hurt us. But let's not forget the inverse square law. Light spreads out as it travels, diluting over the surface area of an expanding sphere. By the time TON 618's light reaches Earth, it's been travelling for 10.8 billion years, spreading across a sphere with a radius of 10.8 billion light-years. The intensity drops dramatically. That's why, despite being one of the universe's brightest objects intrinsically, TON 618, appears as a faint smudge requiring professional telescopes to detect. Distance is the great equalizer. You nestle deeper into your pillow, imagining that flood of radiation blazing outward in all directions, crossing galaxy clusters and voids, a message written in X-rays and ultraviolet light that says, "I am here and I am vast." By the time that message reaches Earth, the sender might be long gone, dimmed or dormant, but the light keeps travelling, a fossil record of a feeding frenzy that happened when the universe was young. Let's talk about TON 618's host galaxy, because surprisingly we know almost nothing about it. The quasar is so absurdly bright that it drowns out the galaxy like a spotlight aimed directly into your eyes. You know there's a stage behind it, but good luck seeing the scenery. When you observe TON 618 through a telescope, what you see is the quasar, a brilliant point source. The host galaxy, with its hundreds of billions of normal stars, is essentially invisible, outshone by the central engine by a factor of hundreds or more. It's like trying to photograph a firefly sitting on the sun. The firefly exists, but your camera won't register it. This is a common problem with high redshift quasars. The quasar emission is so dominant that separating it from the underlying galaxy requires sophisticated techniques, long exposures, adaptive optics to sharpen images, and careful modelling to subtract the quasar's point spread function. Even then, you're often left with ambiguous smudges and low signal-to-noise data. TON 618 is far enough away that pulling off this trick is extraordinarily difficult with current technology. What we do know, or strongly suspect, is that the host galaxy is massive. You don't grow a 66 billion solar mass black hole in a wimpy dwarf galaxy. Supermassive black holes correlate with their host galaxy's properties, specifically the mass of the central bulge. There's an empirical relationship called the M-sigma relation, linking black hole mass to the velocity dispersion of stars in the galactic bulge. Using this relationship in reverse, astronomers estimate that TON 618's host galaxy is probably a giant elliptical, or a massive spiral with a big bulge, something in the range of 1 trillion solar masses in total stellar content. But here's where it gets speculative. TON 618 is being observed at a time when the universe was only about 3 billion years old, and galaxy formation was still messy and chaotic. Galaxies at that epoch were probably less orderly than modern ones. There might have been ongoing mergers, irregular structures, and massive gas reservoirs fueling rapid star formation and black hole growth. The host galaxy could be a train wreck in progress, multiple galaxies colliding and funneling material into the central black hole. Historians still argue whether the host galaxies of the most luminous quasars are fundamentally different from normal galaxies, or just caught in a particularly dramatic phase. The jury's still out. Some observations suggest quasar hosts are often interacting or merging systems, supporting the idea that galaxy collisions trigger quasar activity by dumping gas into the centre. Other studies find quasar hosts that look relatively normal. The truth probably varies case by case. Here's your quirky tidbit. The host galaxy of TON 618 might actually be in the process of self-destructing, or at least radically transforming. Quasar feedback, the radiation and winds we talked about earlier, can heat and expel gas from the galaxy, shutting down star formation. Over millions of years, this could transform a gas-rich spiral galaxy into a red and dead elliptical galaxy, one where star formation has ceased and the stellar population ages passively. TON 618 might be in the act of committing galactic suicide, consuming its own fuel supply and blasting away the rest. There are also hints from simulations that extremely massive black holes like TON 618 can affect their host galaxy's dynamics. The gravitational influence extends outward, possibly slinging stars around or even ejecting them entirely through gravitational interactions. A black hole this massive is like a wrecking ball in the galaxy's centre, and the surrounding stellar population has to reorganise around it. Observationally, we'd love to study the host galaxy in detail, map its stellar populations, measure its star formation rate, look for signs of merger activity, but it's just too hard at this distance. Future telescopes, like the James Webb Space Telescope, or next-generation ground-based observatories with advanced adaptive optics, might tease out more details. But for now, TON 618's host galaxy remains mostly a mystery, defined more by inference and educated guesses than hard data. What we can say is this: the host galaxy provided the raw material that built TON 618. Somewhere in that galaxy's history, enough gas and stars fell into the central region to feed a black hole to 66 billion solar masses. That required either an extraordinarily gas-rich environment, a series of major mergers funneling material inward, or both. It's a galaxy that has been cosmically unlucky, or perhaps lucky depending on your perspective, in having a monster at its heart. There's also the question of what the galaxy looks like now, in its own present, 10.8 billion years after the light we see left it. Has the quasar shut off? Did the black hole run out of food and go dormant? Has the galaxy merged with others, grown larger, or been torn apart? We have no idea. The light we're receiving is ancient news, a postcard from a galaxy that may not even exist in the same form anymore. You imagine that galaxy, a vast island of stars swirling around a central point of light so bright it erases everything nearby. Inside that galaxy, if any planets formed and life evolved, they'd look up at a sky dominated by the quasar's glow, a permanent blinding daylight from the galactic core. Their night would never be truly dark. The quasar would outshine every star, a cosmic reminder that something unimaginably powerful lived at the centre of their universe. Assuming, of course, that the radiation hadn't already sterilised every planet within 1,000 light-years. Sweet dreams. So how did TON 618 get so big? That's the billion-dollar question, literally, given how much funding has gone into studying supermassive black hole growth. Because 66 billion solar masses is not something you accumulate by accident. It requires either extremely efficient feeding, an absurdly long time, or some combination of cosmic factors that astronomers are still trying to untangle. Let's start with the basics. Black holes grow by two primary mechanisms: accretion, eating nearby matter, and mergers, colliding with other black holes. For a black hole like TON 618, both processes probably played a role, but the relative importance of each is still debated. Accretion is the slow and steady method. Gas, dust, and stars wander too close, get captured by gravity, and spiral inward through the accretion disk until they cross the event horizon and add to the black hole's mass. The problem is that accretion has a speed limit. It's called the Eddington limit, and it's the point where the outward radiation pressure from the infalling material equals the inward pull of gravity. Push past the Eddington limit, and the black hole starts blowing away its own food faster than it can eat it. It's a self-regulating mechanism that prevents runaway growth. For a black hole like TON 618, the Eddington-limited accretion rate works out to a few hundred solar masses per year. Sounds like a lot, but even at that rate, growing from a stellar mass black hole, formed from a dying star, maybe 10 to 100 solar masses, to 66 billion solar masses takes an absurdly long time. Plug the numbers into a growth equation, and you'd need billions of years of continuous feeding at maximum capacity. The problem? TON 618 existed when the universe was only 3 billion years old. The timeline is uncomfortably tight. Historians still argue whether black holes in the early universe could exceed the Eddington limit through super-Eddington accretion. Some models suggest that if a black hole is buried deep inside a dense gas cloud, the radiation can't escape efficiently, allowing the black hole to eat faster than it should. Other models propose that early black holes formed from the direct collapse of massive gas clouds starting with masses of thousands or even millions of solar masses right out of the gate, bypassing the slow growth phase entirely. Here's where it gets weird. Some theories suggest that TON 618 might have formed from the merger of several smaller supermassive black holes. When galaxies collide, their central black holes eventually spiral together and merge, combining their masses. If TON 618's host galaxy underwent multiple major mergers during the universe's first few billion years, entirely plausible given how chaotic the early cosmos was, then you could assemble a 66 billion solar mass black hole piecemeal, like building a Lego set one brick at a time, except the bricks are black holes weighing millions or billions of suns each. And then there's the seed black hole problem. Where did the first supermassive black holes come from? You can't grow a 66 billion solar mass monster from a 10 solar mass stellar remnant in the available time, even with optimistic assumptions. So theorists propose two main scenarios. One, light seeds. The first stars, population 3 stars, were massive, short-lived, and collapsed into black holes of 10 to 100 solar masses. These seeds then merged and accreted over time. 2. Heavy seeds. Massive gas clouds in the early universe collapsed directly into black holes of 10,000 to 100,000 solar masses, skipping the star phase entirely. These direct collapse black holes had a big head start. Which scenario applies to TON 618? Nobody knows. Maybe both. Maybe something weirder we haven't thought of yet. The early universe was a wild place, and our models are still educated guesses. Here's your quirky fact. Some simulations suggest that the most massive black holes like TON 618 might have grown through chaotic accretion, where the black hole wanders through its host galaxy, encountering gas clouds and star clusters at random. Instead of sitting quietly at the centre, it actively roams, snacking opportunistically. Over time, dynamical friction drags it back to the galactic core, but not before it's gained significant mass. It's like a cosmic Pac-Man, gobbling pellets while wandering the maze. Let's talk timescales. If TON 618 accreted continuously at the Eddington limit from a 1,000 solar mass seed, it would take roughly 800 million years to reach 66 billion solar masses. That sounds feasible, except the black hole probably didn't feed continuously. Accretion is sporadic, interrupted by periods where the fuel supply runs low or gets blown away by quasar feedback. Include those interruptions, and suddenly the timeline gets tighter. Some researchers think TON 618 must have spent at least half its early life in super Eddington feeding frenzies to hit 66 billion solar masses by age 3 billion. Another complication, black hole spin. As a black hole accretes matter, angular momentum gets transferred, causing the black hole to spin. A rapidly spinning black hole has interesting properties. Its event horizon shrinks slightly, and it can extract energy from the spin via the Penrose process or Blandford-Znajek mechanism. This spin energy can be channeled into jets, we'll get to those soon, which in turn affect the surrounding environment and accretion rate. TON 618's spin is unknown, but it's probably significant, and modelling its growth requires accounting for spin evolution over time. Nobody said black hole astrophysics was simple. You roll over, pulling the blanket higher, and think about the sheer improbability of TON 618. It's not just massive, it's too massive, at least according to the simplest models. Its existence forces us to revise our understanding of early universe conditions, black hole formation, and galactic evolution. It's an outlier that refuses to fit neatly into theory, a cosmic middle finger to anyone who thought they had supermassive black holes figured out. TON 618 poses a problem for cosmologists, and the problem is timing. Finding a 66 billion solar mass black hole when the universe was only 3 billion years old is like finding a senior citizen at a toddler's birthday party. It shouldn't be there, and its presence demands an explanation. The universe began with the Big Bang roughly 13.8 billion years ago. For the first few 100 million years, It was too hot and dense for stars or galaxies to form, just a soup of hydrogen, helium, and dark matter cooling and expanding. The first stars, population 3 stars, ignited maybe 100 to 200 million years after the Big Bang. These were massive metal-free giants that lived fast and died young, collapsing into black holes or exploding as supernovae. From those humble beginnings, you need to grow black holes to millions, then billions, then tens of billions of solar masses. And you need to do it within 3 billion years, because that's when TON 618's light was emitted. 3 billion years sounds like a lot, but on cosmic timescales, it's the blink of an eye. And remember, black hole growth isn't instantaneous. It's limited by accretion rates, fuel supply, and the universe's expansion diluting everything over time. Historians still argue whether the early universe had special conditions that allowed rapid black hole growth. Some models suggest the first galaxies were more gas-rich and compact than modern ones, with dense central regions that efficiently funneled matter into black holes. Others propose that major galaxy mergers were far more common in the early universe, triggering rapid black hole growth through both mergers and merger-induced accretion bursts. Here's your quirky detail. The existence of TON 618 and other ultramassive quasars in the early universe suggests that black hole seeds might have been more massive than we previously thought. If the first black holes were heavy seeds, 100,000 solar masses or more, then growing to 66 billion becomes more plausible. But we don't have direct evidence for these heavy seeds, so it remains speculative. It's a classic, we need this to be true for the math to work situation, which makes theorists nervous. Let's talk about the broader implications. TON 618 isn't alone. Astronomers have found several quasars at high redshifts, meaning seen when the universe was young, hosting black holes with masses in the billions of solar masses. Each one is a puzzle piece suggesting that supermassive black hole growth was extremely efficient in the early universe. Maybe the conditions back then, denser environments, more frequent mergers, less metal pollution in gas clouds, created a perfect storm for black hole growth. There's also the question of how these massive black holes influence their environment. A quasar like TON 618 doesn't just grow passively, it interacts with its surroundings through radiation, winds, and jets. This feedback can heat intergalactic gas, preventing it from cooling and collapsing into new galaxies. In this sense, massive quasars like TON 618 might have shaped the large-scale structure of the universe, acting as cosmic thermostats that regulated galaxy formation. And here's a cosmological twist. TON 618's light has been travelling for 10.8 billion years to reach us, meaning we're seeing it as it was in the early universe. But the universe's expansion has stretched space itself during that time. The comoving distance to TON 618, the distance accounting for expansion, is about 18 billion light-years. This distinction matters when you're trying to map the universe's structure and evolution. TON 618 isn't just far, it's far in a way that requires general relativity and cosmological models to properly describe. Let's get philosophical for a moment. The existence of TON 618 challenges our assumptions about how quickly complexity can arise. In just 3 billion years, the universe went from primordial simplicity, hydrogen and helium gas, to hosting galaxies with supermassive black holes that outshine everything around them. That's a remarkably short timescale for such dramatic transformation. It's like the universe speedran its adolescence, skipping awkward phases and jumping straight to full-blown cosmic puberty. Some researchers speculate that TON 618 might have been even more massive in the past, and has since lost mass through Hawking radiation, a quantum process where black holes slowly evaporate by emitting particles. But Hawking radiation is negligibly slow for black holes this massive. TON 618 would take something like 100 years to evaporate completely, far longer than the current age of the universe. So no, TON 618 hasn't shrunk. If anything, it's probably still growing, assuming it still has a food supply. Another angle, TON 618's existence constrains models of dark matter and dark energy. The growth of supermassive black holes depends on the availability of baryonic matter, normal atoms and molecules. If the early universe had significantly different ratios of dark matter to normal matter, or if dark energy behaved differently back then, it could affect how efficiently black holes grew. TON 618 is a data point that cosmologists plug into their simulations, tweaking parameters until the models spit out something that matches observations. You let your mind drift, imagining the universe as a toddler, barely 3 billion years old, already producing monsters like TON 618. It's a reminder that the cosmos doesn't follow human intuition. Things happen faster or slower, larger or smaller than we expect. The universe plays by its own rules, and objects like TON 618 exist because the math allows it, regardless of whether our brains can comfortably process the implications. Studying TON 618 is an exercise in frustration and ingenuity, because almost everything about it is designed to make astronomers' lives difficult. It's incredibly distant, obscenely bright, and surrounded by an accretion disk that drowns out subtle details. Observing it requires stitching together data from multiple wavelengths, telescopes, and observing campaigns, all while accounting for the universe's expansion, redshift, and light travel time. Let's start with the distance problem. TON 618 is 10.8 billion light-years away, which means the light reaching Earth is faint despite the quasar's intrinsic brightness. The inverse square law is brutal. Light intensity drops with the square of the distance. Even though TON 618 is one of the most luminous objects in the universe, by the time its light crosses 10.8 billion light-years, it's diluted to a faint signal that requires large telescopes and long exposure times to detect. And it's not just faintness. The light is also redshifted. Because the universe has been expanding while the light was in transit, the wavelengths have been stretched. TON 618 has a redshift, Z, of about 2.219, meaning observed wavelengths are roughly 3.2 times longer than emitted wavelengths. Ultraviolet light emitted by the quasar arrives here as visible or near-infrared light. Optical light becomes infrared. This requires astronomers to observe across multiple wavebands to reconstruct the full spectrum. Compounding the issue is the accretion disk's brightness. The disk emits so intensely that it overwhelms the host galaxy, making it nearly impossible to study the galaxy's stellar population or structure. Techniques like quasar subtraction, modelling the quasar's light and digitally removing it, help, but they're imperfect. You're left with residuals, noise, and ambiguous smudges that might be the galaxy or might be artifacts. Historians still argue whether we'll ever get a clear image of TON 618's host galaxy without next-generation telescopes. The James Webb Space Telescope, with its infrared sensitivity and high resolution, is expected to help. But even JWST has limits. TON 618 is at the edge of its reach, and separating quasar light from galaxy light will require careful modelling and long integration times. Here's your quirky fact. TON 618 was discovered using photographic plates, physical pieces of glass coated with light-sensitive emulsion. An astronomer would expose the plate to the sky for hours, develop it like old-school film, and examine it under a microscope. Finding TON 618 involves spotting a faint smudge among thousands of other smudges, then following up with spectroscopy to determine what it was, is almost quaint compared to modern digital surveys that process terabytes of data automatically. Modern observations involve coordinating multiple facilities. Radio telescopes like the Very Large Array, VLA, map the quasar's radio emission, revealing information about jets and magnetic fields. Optical telescopes like those at the Keck Observatory or the European Southern Observatory capture visible and near-infrared light, studying the accretion disk and broadline region. X-ray satellites like Chandra or XMM Newton observe high-energy emission from the disk's hot inner regions. Each wavelength tells a different part of the story. Spectroscopy is crucial. By spreading TON 618's light into a spectrum, essentially a rainbow of wavelengths, astronomers can identify emission and absorption lines caused by atoms in the accretion disk and surrounding gas. These lines reveal the disk's composition, temperature, velocity, and density. They also allow precise measurement of the redshift, which in turn gives the distance and look-back time. But there are technical challenges. The Earth's atmosphere absorbs and distorts light, especially in the infrared and ultraviolet. Ground-based telescopes need adaptive optics, systems that use deformable mirrors to counteract atmospheric turbulence in real time to achieve sharp images. Even then, some wavelengths are only accessible from space, requiring expensive satellite missions. Timing is another issue. TON 618 might vary in brightness over timescales ranging from days to years. Catching those variations requires repeated observations spaced over time, but telescope time is precious and oversubscribed. Astronomers compete fiercely for access. A comprehensive monitoring campaign of TON 618 might require dozens of nights spread over several years, coordinating multiple facilities and teams. It's logistically complex and expensive. Then there's the data processing. Raw telescope data is messy, filled with instrumental artifacts, cosmic rays, atmospheric effects, and noise. Extracting meaningful measurements requires calibration, comparing the target to standard stars, correcting for detector quirks, and applying statistical techniques to boost signal-to-noise ratios. For an object like TON 618, you might spend months processing a single night's worth of data. Let's not forget theoretical modelling. Observations alone don't tell the full story. You need models to interpret them. Researchers build simulations of accretion disks, jets, and black hole environments, then compare synthetic observations from the models to real data. If they match, great. If not, back to the drawing board. TON 618's extreme parameters push these models to their limits, testing whether our understanding of black hole physics holds up in the most extreme environments. There's also the issue of cosmic obscuration. Dust and gas between Earth and TON 618 can absorb and scatter light, dimming the quasar and altering its spectrum. Disentangling intrinsic properties from intervening effects requires careful analysis and assumptions about the intergalactic medium's composition. Get it wrong, and your measurements of TON 618's luminosity, mass, or accretion rate will be off. You imagine the armies of astronomers, engineers, and data analysts working to squeeze information out of those faint photons that travelled 10.8 billion years. Each observation is a triumph of technology and patience, a collaborative effort spanning continents and decades. And despite all that effort, TON 618 remains stubbornly mysterious, revealing itself grudgingly, one puzzle piece at a time. Now let's talk about the jets, because TON 618 isn't content with just being massive and bright. It also fires relativistic particle beams into space like a cosmic sniper rifle. These jets are among the most extreme phenomena in astrophysics, and they're powered by the black hole's rotation and magnetic fields, in a process that's still not fully understood. Here's how it works. In simplified terms, the accretion disk around TON 618 is threaded with magnetic field lines. As the disk rotates, these field lines get twisted and wound up, forming tightly coiled structures near the black hole's poles. Charged particles, electrons, protons, ions, get caught in these magnetic fields and accelerated to nearly the speed of light. The particles spiral along the field lines and get funneled outward in narrow, focused beams perpendicular to the accretion disk. These are the jets. The speeds are ludicrous. Particles in the jets are travelling at 99% the speed of light or more, carrying enormous amounts of kinetic energy. The jets extend outward for thousands, sometimes hundreds of thousands, of light years, far beyond the host galaxy, ploughing through intergalactic space and creating shock waves and lobes of glowing plasma. It's like the black hole is firing a cosmic blowtorch into the void, and the void is losing. Historians still argue whether all supermassive black holes produce jets, or only those with specific conditions: high spin rates, strong magnetic fields, or particular accretion geometries. The current thinking is that jets require a rapidly spinning black hole and a well-organised magnetic field threading the disk. TON 618 likely checks both boxes, given its mass and feeding rate. Here's your quirky detail. The mechanism behind jet formation is called the Blandford-Znajek process, named after the physicists who modelled it in the 1970s. It's essentially a way to extract rotational energy from the black hole itself. The spinning black hole drags space-time around it, a phenomenon called frame dragging, and this rotation twists magnetic field lines, generating electric currents that accelerate particles. It's like the black hole is a giant dynamo, converting its spin into electromagnetic energy and firing it outward. The jets also emit synchrotron radiation, light produced when charged particles spiral in magnetic fields. This radiation is brightest in the radio wavelengths, which is why many quasars, including TON 618, are strong radio sources. The radio emission traces the jet structure, revealing knots, bends and hotspots where the jet collides with surrounding gas. Radio telescopes can map these features, providing a window into the jet's physics. But the jets don't just carry energy, they carry matter. Gas and plasma are ejected along with the relativistic particles, and over time, this can amount to a significant mass loss from the system. Some estimates suggest that jets can carry away as much as 10% of the infalling matter, meaning the black hole effectively wastes a portion of its meal by flinging it into space at near light speed. It's inefficient, but the universe doesn't care about efficiency. Let's talk about what happens when these jets hit something. As they plough through intergalactic gas, they create shocks, regions where the jet's kinetic energy is converted into heat and turbulence. These shocks heat the gas to millions of degrees, causing it to glow in X-rays. Over time, the jets carve out enormous cavities in the surrounding medium, creating bubble-like structures that can be hundreds of thousands of light-years across. These radio lobes are visible in radio surveys as diffuse clouds of emission surrounding quasars. In TON 618's case, we don't have detailed observations of its jets yet, partly because of its distance, partly because the quasar's core emission is so bright it overwhelms the fainter jet emission. But based on comparisons with other massive quasars, TON 618 almost certainly has jets, and they're probably among the most powerful in the universe. The energy output in the jets alone could rival the luminosity of entire galaxies. And here's where it gets cosmically consequential. Those jets affect galaxy evolution. By pumping energy into the surrounding gas, they heat it, preventing it from cooling and collapsing to form new stars. This is part of the quasar feedback mechanism we mentioned earlier. The jets, combined with radiation pressure from the accretion disk, can regulate star formation across the host galaxy, and even in neighbouring galaxies. TON 618's jets might have shaped the distribution of matter over millions of light-years, leaving a lasting imprint on the large-scale structure of the universe. There's also a directional effect. If you happen to be looking down the barrel of one of TON 618's jets, if the jet is pointed almost directly at Earth, the jet appears much brighter due to relativistic beaming, a consequence of particles moving near light speed toward you. Fortunately, or unfortunately depending on your perspective, TON 618's jets aren't pointed at us, so we don't see this extreme boosting effect. But other quasars, called blazars, are oriented such that their jets point earthward, making them some of the brightest and most variable objects in the sky. You imagine those jets, twin spears of light and matter lancing outward from TON 618, cutting through space for eons, invisible to the naked eye but blazing in radio telescopes. They're remnants of the black hole's feeding frenzy, exhaust from the universe's most powerful engine, and they'll keep streaming outward long after TON 618 itself has gone quiet. Fossil records of a time when the black hole ruled its corner of the cosmos. Let's map the sphere of doom around TON 618, the region where its gravity dominates absolutely and nothing escapes its influence. This isn't just the event horizon. that's the point of no return. We're talking about the broader gravitational influence, the radius within which TON 618's pull is the dominant force, dictating the motion of stars, gas, and anything unlucky enough to wander nearby. Gravitational influence scales with mass and falls off with distance. For a black hole, you can define an influence radius, the distance at which the black hole's gravity starts to significantly affect the motion of stars in the surrounding galaxy. For TON 618, with 66 billion solar masses, this influence radius is enormous, potentially spanning thousands of light years. Stars within this zone don't orbit the galaxy as a whole, they orbit the black hole directly, their trajectories bent and twisted by the central mass. Inside the influence radius, stellar dynamics get weird. Stars move faster than you'd expect from the galaxy's overall gravitational field. They zip around in highly eccentric orbits, occasionally getting flung outward at high speeds or, less fortunately, spiraling inward toward the black hole. This region is called the sphere of influence, and it's a zone of gravitational chaos. Historians still argue about the exact size of TON 618's sphere of influence because it depends on the host galaxy's properties, which we don't know precisely. But rough estimates, based on scaling relations, suggest it could extend anywhere from 1,000 to 10,000 light-years. For comparison, the Milky Way's supermassive black hole, Sagittarius A star, has an influence radius of about 2 to 3 light-years. TON 618's sphere of influence is orders of magnitude larger. Here's your quirky fact. Within the sphere of influence, the concept of a stable planetary orbit becomes tenuous. If a star with planets wanders into this region, the tidal forces from the black hole can disrupt planetary orbits, flinging planets into interstellar space or sending them plunging into the star. Over millions of years, any planetary systems that venture too close to TON 618 would be shredded or scattered. It's a no-man's land for solar systems. Now let's talk tidal radius, the distance at which tidal forces from the black hole overcome an object's self-gravity and tear it apart. For a star like the Sun approaching TON 618, the tidal radius is several hundred million kilometers, depending on the star's density. Cross that threshold, and the star gets stretched into a stream of gas in a process called tidal disruption. The gas then forms a temporary accretion disk around the black hole, producing a bright flare of radiation as the star's remains spiral inward. These tidal disruption events are dramatic, short-lived phenomena that astronomers occasionally observe in distant galaxies. For TON 618, the tidal radius is farther out than you'd expect. Because the black hole is so massive, the tidal forces near the event horizon are actually relatively gentle, a consequence of the horizon's enormous size. If you could somehow hover near the event horizon in a spaceship, ignoring radiation, heat, and the impossibility of hovering, you wouldn't be immediately ripped apart. The tidal gradient, the difference in gravitational pull between your head and feet, would be small. You'd cross the horizon almost peacefully, only to be torn apart deeper inside where space-time curvature gets steeper. It's a deceptively gentle approach to certain doom, but farther out, say at the accretion disk's outer edge or in the surrounding stellar environment, tidal effects are significant. Stars passing within a few billion kilometers could be stretched and distorted, even if they don't fully disrupt. Close binary star systems could be torn apart, with one star captured by the black hole and the other flung away at high speed. These hypervelocity stars are occasionally detected fleeing galaxies at speeds exceeding the galactic escape velocity, and tidal interactions with supermassive black holes are one proposed explanation. Let's also consider the photon sphere, the radius at which gravity is strong enough to bend light into closed orbits. For a non-rotating black hole, the photon sphere sits at 1.5 times the Schwarzschild radius. For TON 618, that's roughly 295 billion kilometers, or about 2,000 astronomical units. At this distance, light literally orbits the black hole. If you were floating at the photon sphere and looked sideways, You'd see the back of your own head, light having travelled around the black hole to reach your eyes. It's a mind-bending consequence of extreme space-time curvature. Within the photon sphere, stable orbits are impossible even for light. This is the boundary between you might escape if you're moving fast enough and nope, you're doomed. Anything inside this radius that isn't already falling directly inward is essentially trapped. It's the final warning zone before the event horizon. You nestle deeper into your blankets, thinking about those nested shells of influence. The outer sphere where stars' orbits get scrambled, the tidal radius where objects get shredded, the photon sphere where even light can't escape sideways, and finally the event horizon, the ultimate one-way door. Each layer represents a threshold, a point where the physics shifts and new horrors become possible. TON 618 is surrounded by concentric zones of escalating danger, like a cosmic onion made of gravitational nightmares. And somewhere in the middle of all that, silent and invisible, sits the singularity, a point where all that mass is compressed to infinite density, where space-time curvature becomes infinite, and where the laws of physics as we know them simply stop working. It's the final mystery, hidden behind the event horizon, forever beyond our ability to observe or understand. So let's talk about spaghettification, because if you're going to understand what TON 618 would actually do to your body, you need to embrace the absurdity of tidal forces and the fact that gravity doesn't pull uniformly. It pulls harder on the parts of you that are closer. Imagine you're falling feet first toward TON 618. You're still far from the event horizon, maybe a few million kilometers out, drifting through space in your doomed trajectory. At first, nothing feels wrong. You're in free fall, weightless, floating peacefully like an astronaut. But then you start to notice something odd. Your feet feel heavy. Not heavy like they're being pulled down, but heavy like they're being pulled away from your body. This is tidal force in action. Gravity follows an inverse square law. It gets stronger as you get closer to the source. Your feet, being slightly closer to TON 618 than your head, experience slightly stronger gravitational pull. At normal distances, this difference is negligible. But as you approach a black hole, especially in the final stages, that difference becomes significant. Your feet are being pulled harder than your head, and the net effect is a stretching force along the length of your body. The term spaghettification was coined by Stephen Hawking, and it's delightfully accurate. As tidal forces increase, you get stretched like pasta dough, elongated along the direction of the gravitational gradient. Simultaneously, you're compressed from the sides, squeezed inward as your body tries to follow the converging gravitational field lines. You become longer and thinner, a human noodle spiraling toward oblivion. But here's the weird part about TON 618 specifically. Because it's so massive, the tidal forces near the event horizon are surprisingly gentle. For smaller black holes, stellar mass black holes with maybe 10 solar masses, you'd be spaghettified long before reaching the event horizon. The tidal gradient would rip you apart while you're still thousands of kilometers out. But TON 618's event horizon is so enormous, 195 billion kilometers in radius, that the curvature of space-time at the horizon is relatively gradual. Historians still argue about the exact threshold, but calculation suggests that for a black hole of TON 618's mass, a human could actually cross the event horizon intact. You'd feel tidal forces, sure, but they wouldn't be immediately lethal. You'd drift across that invisible boundary, passing the point of no return, and for a brief moment, maybe seconds, maybe minutes depending on your trajectory, you'd still be recognizably human. But don't get comfortable. Once you're inside the event horizon, the tidal forces only increase as you approach the singularity. The gradient gets steeper, the stretching more extreme, and eventually, inevitably, you reach a point where the forces exceed your body's structural integrity. Your bones snap, your muscles tear, your cells rupture. You're no longer a person, you're a stream of disassociated atoms, stretched into a thin filament spiraling inward. Here's your quirky fact. The process wouldn't be instantaneous. Depending on your distance from the singularity and your infall speed, spaghettification could take anywhere from milliseconds to minutes. You'd be conscious for at least part of it, assuming the radiation and heat haven't already killed you. Your brain, still receiving signals from nerve endings, would register the sensation of being pulled apart, though pain might not be the right word. It's unlikely human neurology has a framework for this experience. Let's talk numbers. The tidal force on your body is proportional to your height times the mass of the black hole, divided by the cube of your distance from the centre. As you fall inward, that distance cubed term in the denominator shrinks rapidly, causing the tidal force to skyrocket. By the time you're within a few thousand kilometres of the singularity, still far in absolute terms but close in gravitational terms, the tidal force could be millions of times stronger than Earth's surface gravity. Your body wouldn't resist, nothing would, and it's not just you. Anything falling into Ton 618 experiences the same fate. Asteroids get stretched into rubble streams, gas clouds elongate into filaments, even light in a sense experiences tidal effects. Photons following geodesics through the warped space-time get stretched in wavelength, redshifted toward oblivion as they spiral inward. There's a point, somewhere deep inside the event horizon, called the singularity. General relativity predicts it's a point of infinite density, where the curvature of space-time becomes infinite and the math breaks down. But you'd never reach it as a coherent object. The tidal forces would dismantle you atom by atom, electron by electron long before you got there. By the time your constituent particles approach the singularity, you're not even particles anymore. You're information, quantum states, abstract mathematical entities that the universe has trouble keeping track of. Interestingly, from an outside observer's perspective, you never actually cross the event horizon. Due to gravitational time dilation, which we'll get to in the next section, time slows down for you as you approach the horizon. To someone watching from a safe distance, you appear to slow down, freeze, and fade away. Your image red-shifted into invisibility. You're smeared across the event horizon for eternity, at least from their point of view. From your perspective, of course, you cross the horizon and experience spaghettification in finite time. Relativity is funny that way. Let's also consider rotation. If TON 618 is spinning, and it probably is, then the space-time inside the event horizon is dragged around with the black hole. This frame-dragging effect means that as you fall inward, you're not just falling straight down, you're also being forced to rotate with the black hole. Your trajectory spirals, corkscrewing inward, adding a rotational component to your spaghettification. You'd be stretched, compressed, and twisted simultaneously. It's less like pasta, and more like taffy being pulled and spun on a cosmic taffy machine. You shift under the blankets, imagining that slow, inexorable stretch, the sensation of your body elongating, the awareness fading as neural connections snap and consciousness dissolves. It's a strangely peaceful image, in a grotesque sort of way. Becoming part of the black hole, your atoms added to its mass, your information encoded somehow in the quantum structure of the event horizon. You'd become one with Ton 618, a footnote in its incomprehensible existence, and honestly there are worse ways to go. Now let's discuss time dilation near Ton 618, because this is where general relativity stops being abstract math and starts being existentially disturbing. Time, that steady constant you've relied on your entire life, becomes slippery and relative near a black hole. Clocks slow down, lifetimes compress, and the universe outside ages at a terrifying pace while you're frozen in near stasis. The fundamental principle is this: the stronger the gravitational field, the slower time passes. This is called gravitational time dilation, and it's a consequence of how mass warps space-time. Near TON 618, space-time is severely warped, and clocks tick slower the closer you get to the event horizon. At the event horizon itself, time dilation becomes infinite. From an outside observer's perspective, time stops completely. Here's a thought experiment. You and a friend decide to explore Ton 618. Your friend stays in a spaceship at a safe distance, say a few billion kilometers out, while you take a smaller craft and descend toward the event horizon. You're equipped with a clock that sends a signal back to your friend every second, according to your clock. As you descend, your friend notices something odd. The signals from your clock start arriving slower. What began as one signal per second becomes one signal every 2 seconds, then every 5 seconds, then every minute. Your clock, from their perspective, is slowing down. By the time you approach within a few thousand kilometers of the event horizon, your friend is receiving signals once per hour, then once per day, then once per year. You appear to be moving in extreme slow motion, frozen like a statue falling through molasses. But from your perspective, nothing is wrong. Your clock ticks normally, you breathe normally, time passes at its usual rate. You approach the event horizon and cross it in finite time, maybe a few minutes, maybe an hour, depending on your trajectory. You're unaware that from your friend's viewpoint, you've been falling for centuries, millennia, eons. You're experiencing time at a different rate, and relativity says both perspectives are valid. Historians still argue about whether this time dilation has practical implications for exploring black holes. In theory, you could use a black hole as a time machine, not to the past, but to the future. Descend close to the event horizon, hover there for what feels like a year, ignoring the radiation and tidal forces, then ascend back to safety. When you return, centuries or millennia might have passed in the outside universe. You'd have jumped forward in time, aging only a year while the rest of reality aged much longer. Of course, this only works if you can hover near the event horizon without falling in, which requires enormous amounts of energy to counteract the gravitational pull. And you'd better hope civilization still exists when you return, because there's no coming back if the universe outside has moved on without you. Here's your quirky fact. Gravitational time dilation has been measured on Earth. Atomic clocks placed at different altitudes, one at sea level, one on a mountain, tick at slightly different rates. The difference is minuscule, a few nanoseconds per day, but it's measurable and matches general relativity's predictions perfectly. GPS satellites have to account for time dilation because they're farther from Earth's gravitational well and experience time slightly faster than clocks on the surface. Without these corrections, GPS would drift and become inaccurate within hours. Near TON 618, the effect is incomparably stronger. Let's say you're orbiting just outside the event horizon, at the innermost stable circular orbit, the SCO. At this distance, time dilation is severe, maybe 50% or more. For every hour you experience, 2 or more hours pass in the distant universe. Stay there for a day, and weeks pass outside. Stay for a year, and decades elapse. And if you somehow descended closer, riding the edge of stability, the dilation increases further. At twice the Schwarzschild radius, time runs at about 70% normal speed. At one point, 5 times the radius, it's less than 50%. Approach the horizon itself, and time dilation approaches infinity. 1 second for you could correspond to years, centuries, or millennia outside. You'd be untethered from the universe's timeline, adrift in a pocket of slow time. This has bizarre implications for anything orbiting or falling into Ton 618. Material in the inner accretion disk experiences significant time dilation. From our distant perspective, processes in the disk are slowed. But from the disk's perspective, it's the outside universe that's fast-forwarding. Stars living and dying in what seems like rapid succession. The quasar exists in a different temporal regime, its processes stretched or compressed depending on your frame of reference. Let's go deeper, literally. Suppose you cross the event horizon. Once inside, the roles of space and time swap in a sense that's difficult to articulate without math. Moving toward the singularity is no longer a spatial choice, it's a temporal inevitability. The singularity isn't a place you can avoid by steering left or right, it's in your future, as unavoidable as next Tuesday. You're falling forward in time as much as inward in space, and the singularity is the endpoint of that timeline. From the outside, you never finish crossing the horizon. Your image freezes, redshifts and fades, asymptotically approaching the boundary but never quite crossing. To the universe, you're stuck at the event horizon forever, a smeared-out quantum ghost. But you don't experience it that way. You cross, you fall, and you reach the singularity in finite proper time. Both descriptions are true, depending on the reference frame. Relativity doesn't resolve the paradox. It just tells you both perspectives are valid. There's also the issue of causality. Inside the event horizon, all causal paths, every possible trajectory, lead to the singularity. You can't send signals out, can't reverse course, can't do anything except move forward toward the inevitable end. The singularity is in the future of every event inside the horizon, a final convergence point where all timelines terminate. You close your eyes, imagining two clocks, one falling, one watching. The falling clock ticks steadily, measuring seconds, minutes, hours. The watching clock races ahead, days and years blurring past. Both clocks are right. Both measure time accurately from their perspective. And that, more than the tidal forces or the radiation or the impossible scale, is the truly unsettling part. Time itself is negotiable, flexible, a variable that depends on where you are and how fast you're moving. TON 618 doesn't just distort space, it distorts time, and by extension it distorts reality. Let's bring this closer to home by comparing TON 618 to Sagittarius A star, the supermassive black hole sitting quietly at the centre of our Milky Way galaxy. Because once you put them side by side, you realise just how cosmically outclassed our local black hole is. It's like comparing a hamster to an elephant, except the size difference is even more extreme. Sagittarius A star, often abbreviated as SGR A star, has a mass of about 4.1 million solar masses. That's already mind-bogglingly massive by human standards. It's over 4 million times heavier than the Sun, and it sits roughly 26,000 light-years from Earth, anchoring the gravitational centre of our galaxy. We've observed stars orbiting it at speeds exceeding 5,000 kilometers per second, their trajectories tracing out ellipses that prove something incredibly massive and compact is lurking there. TON 618, by comparison, weighs in at 66 billion solar masses. That's over 16,000 times more massive than S-Gray star. If S-Gray star were a marble, TON 618 would be a boulder the size of a house. The mass ratio is so extreme that it's almost comical. Let's compare event horizons. SGR A star's event horizon has a radius of about 12 million kilometers, or roughly 0.08 astronomical units. That's roughly 17 times the radius of the Sun. You could fit the Sun comfortably inside Sagittarius A star's event horizon with room to spare. It's big, but still graspable in solar system terms. TON 618's event horizon radius, as we've established, is about 195 billion kilometers, or 1,300 astronomical units. That's over 16,000 times larger than S-Gray star by radius. You could fit S-Gray star's event horizon inside TON 618's event horizon thousands of times over. In fact, you could fit our entire solar system, Sun, planets, Kuiper belt, inside TON 618 multiple times, and still have room left. Historians still argue about whether size or mass is the more meaningful comparison for black holes, but ultimately they're correlated. More mass means a larger event horizon, and both contribute to gravitational influence and tidal effects. By either measure, TON 618 dwarfs Sagittarius A star. Here's your quirky fact: we've actually imaged SGR A star. In 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A star, showing a glowing ring of emission around a dark central shadow, the photon ring and event horizon. It was a monumental achievement, requiring coordinating radio telescopes across the globe to create a virtual Earth-sized telescope with enough resolution to image something 26,000 light-years away and only 12 million kilometers wide. Imaging TON 618's event horizon is currently impossible. It's over 400 times farther away than Esca A star, and despite being much larger, the angular size, the apparent size from Earth, is far too small for current instruments. You'd need a telescope array spanning the solar system or beyond to have any hope of resolving TON 618's event horizon. Maybe in a few centuries, if we build space-based interferometers, we'll get a picture. For now, it remains an abstraction, inferred from indirect measurements. Let's talk about gravitational influence. SGR-A star dominates the dynamics of stars within a few light-years of the galactic center. Beyond that, the collective gravity of all the stars in the galaxy takes over, and Sagittarius A star becomes just one contributor among many. Its sphere of influence is roughly 2 to 3 light-years in radius. TON 618's sphere of influence, as we discussed, extends thousands of light-years. It affects stellar dynamics across a significant fraction of its host galaxy. Stars that wander into this zone have their orbits permanently altered, and the black hole's gravity can shape the structure of the galactic core over millions of years. Now let's consider luminosity. SGR-A star is currently pretty quiet. It's not actively feeding at a high rate, so it's not particularly bright. The emission we detect from it is relatively faint, mostly radio waves from the hot gas swirling in the accretion flow, and occasional X-ray flares when something gets too close and heats up. Sagittarius A star is, by quasar standards, asleep. TON 618 is a raging inferno by comparison. Its luminosity is 100 trillion times greater than the Sun, pumping out energy across the electromagnetic spectrum. If you replace Sagittarius A star with TON 618, the Milky Way's center would become the brightest object in the galaxy by far, outshining all 200 to 400 billion stars combined. The radiation would sterilize planets within thousands of light-years, ionize gas clouds, and fundamentally alter the galaxy's structure. Earth, sitting 26,000 light-years away, would probably be irradiated enough to strip the atmosphere and boil the oceans. It wouldn't be instant, but over thousands of years, life on Earth would be extinguished. There's also the feeding rate. SGR-A star accretes material at a trickle, maybe a few hundredths of an Earth mass per year. It's starving, with very little gas or dust nearby to consume. The Milky Way's central region has been swept relatively clean over billions of years. TON 618, in its active quasar phase, is consuming hundreds of solar masses per year. It's gorging, feasting on a seemingly endless supply of gas funneled inward by its massive accretion disk. This difference in feeding rate is why TON 618 is a quasar and SGR-A star is dormant. Give SGR-A star a massive supply of gas, say, by colliding the Milky Way with another galaxy, and it could light up as a quasar too, but right now it's on a starvation diet. Let's personalize it. Sagittarius A star is our black hole. It's been sitting at the galactic center for most of the Milky Way's history, quietly anchoring the galaxy's structure. It's part of our cosmic neighborhood, and we've studied it extensively. We know stars that orbit it, we've imaged it, and we monitor it regularly. It's familiar, almost friendly in its dormancy. TON 618 is alien, distant, and unimaginably more powerful. It's a glimpse into what SGR-A star might have been like billions of years ago when the Milky Way was young and gas-rich. Or maybe Sagittarius A star was never that extreme. Maybe TON 618 is an outlier, a freak of cosmic evolution that grew beyond normal limits. Either way, the comparison puts our local black hole in perspective. Esca star is massive and fascinating, but TON 618 is on another level entirely. You roll onto your side thinking about Sagittarius A star, that quiet giant lurking at the heart of our galaxy, and then TON 618, the distant monster blazing across the early universe. One is a neighbour you've learned to live with, The other is a cosmic horror you're grateful exists only in telescopes and imagination, safely separated by over 10 billion light-years of expanding space. So what happens to TON 618 in the long run? Does it keep growing forever, eventually consuming entire galaxy clusters? Does it evaporate into nothingness? Or does something weirder happen? Let's explore the possible futures for this cosmic behemoth, keeping in mind that future is a tricky word when we're already seeing it 10.8 billion years in the past. First, the growth scenario. Right now, or rather 10.8 billion years ago, TON 618 is actively feeding, gobbling up gas and stars at a prodigious rate. But this can't last forever. Quasars are a phase, not a permanent state. Eventually one of two things happens. The black hole runs out of nearby fuel, or it blows away its own food supply through quasar feedback. The feedback mechanism is relentless. As TON 618 feeds, it emits radiation and drives winds that heat and expel gas from the surrounding region. Over time, this creates a dead zone around the black hole, a region swept clean of material. The accretion rate drops, the quasar dims, and TON 618 transitions into a quieter state, more like Sagittarius A star. This process probably takes millions to tens of millions of years, but cosmically, that's a blink. Once the quasar phase ends, TON 618 doesn't disappear, it just goes dormant. The black hole is still there, still 66 billion solar masses, or more if it's grown since the light we're seeing left. It's just not actively feeding. It sits at the galactic centre, a gravitational anchor, quietly influencing the orbits of nearby stars but no longer lighting up the cosmos. Historians still argue whether supermassive black holes can reignite after going dormant. The answer is yes, if new fuel arrives. A galaxy merger, for instance, can funnel fresh gas into the centre, triggering a new episode of quasar activity. TON 618 might have experienced multiple cycles of feeding and dormancy over its lifetime, flickering on and off like a cosmic light bulb as gas supplies wax and wane. Here's your quirky fact. In the far future, trillions of years from now, galaxy mergers will become less common as the universe's expansion accelerates. Galaxies will become increasingly isolated, and supermassive black holes will have fewer opportunities to refuel. TON 618, along with every other black hole, will enter a long period of starvation, sitting idle in the centres of aging galaxies. Now let's talk about the really long-term fate, Hawking radiation. In 1974, Stephen Hawking showed that black holes aren't entirely black. Due to quantum effects near the event horizon, black holes emit a faint thermal radiation, slowly losing mass over time. This process is called Hawking radiation, and it means that black holes eventually evaporate. But, and this is a big but, the timescale for a black hole like TON 618 to evaporate is preposterously long. The evaporation timescales with the cube of the black hole's mass. For a stellar mass black hole, say 10 solar masses, evaporation takes about 10 to the power of 67 years. For TON 618, with 66 billion solar masses, the evaporation time is roughly 10 to the power of 99 years. That's a one followed by 99 zeros. For comparison, the current age of the universe is about 10 to the power of 10 years, a one followed by 10 zeros. TON 618 will outlive the universe's current age by a factor of 10 to the power of 89. It's not just a long time, it's a cosmologically meaningless timescale, so far in the future that the universe will be unrecognisable. By the time TON 618 begins to significantly evaporate, the universe will be in its black hole era, a distant epoch where stars have burned out, galaxies have dispersed, and black holes are the dominant remnants. The universe will be cold, dark, and nearly empty, with only the faint glow of Hawking radiation providing any light. TON 618 will sit in this void, slowly radiating away its mass, one photon at a time, over timescales that make billions of years look like nanoseconds. And here's where it gets weird. As TON 618 evaporates, it shrinks. A smaller black hole has a higher Hawking temperature, it radiates faster. In the final stages, when TON 618 has shrunk down to relatively small mass, still millions of solar masses, the evaporation accelerates. The last few percent of mass disappear in a flash, a burst of radiation as the black hole finally winks out of existence. What's left? Maybe nothing. Maybe a remnant of exotic particles. Maybe a naked singularity, if quantum gravity behaves strangely. We don't know, because the physics at that scale is beyond our current theories. Let's consider another scenario. Black hole mergers. If TON 618's host galaxy merges with another galaxy containing a supermassive black hole, the two black holes will eventually spiral together and merge. This would produce an even more massive black hole and emit gravitational waves, ripples in space-time, so powerful that they'd be detectable across the universe. The merger would be one of the most energetic events possible, briefly outshining entire quasars in gravitational wave luminosity. Current observations suggest that black hole mergers are common in the universe's history. TON 618 might have already merged with other black holes to reach its current mass. And in its future, relative to the light we're seeing, it might merge again, growing even larger. There might be black holes out there in the present-day universe that started as TON 618 level monsters and merged into even more absurd masses. We haven't found them yet, but they could exist. There's also the cosmological endgame. If the universe's expansion continues to accelerate, driven by dark energy, then eventually galaxies outside our local group will recede beyond the cosmic horizon, unreachable and unobservable. TON 618, already distant, will drift farther and farther away in comoving coordinates, its light stretched to undetectable wavelengths. It will vanish from our observable universe, not because it's gone, but because the expansion has carried it beyond the horizon of what we can ever see. You pull the blanket up to your chin, thinking about TON 618's future. Dormancy, mergers, eventual evaporation over timescales that dwarf comprehension. It's a reminder that even the most powerful objects in the universe are temporary. Nothing lasts forever, not even a 66 billion solar mass black hole. Given enough time, everything fades, evaporates, or drifts away. TON 618 will outlive stars, galaxies, and probably civilizations. But even it has an expiration date, written in the faint equations of quantum mechanics and general relativity. Let's talk about gravitational waves and how future observatories might catch TON 618 doing something dramatic, like colliding with another supermassive black hole. Because if you think TON 618 is impressive sitting still, wait until you hear about the fireworks it could produce if it merged with a peer. Gravitational waves are ripples in space-time itself, produced when massive objects accelerate asymmetrically. Einstein predicted them in 1916 as a consequence of general relativity, but they're so faint that detecting them took a century of technological development. In 2015, the LIGO Observatory made the first direct detection of gravitational waves, catching the merger of two stellar mass black holes about 1.3 billion light-years away. The signal lasted less than a second, a brief chirp as the black holes spiraled together and merged. Now imagine scaling that up to supermassive black holes. When two black holes like TON 618 merge, they produce gravitational waves so powerful they warp space-time across the observable universe. The energy released in gravitational waves alone can exceed the total light output of every star in the universe combined, briefly making the merger the single most energetic event occurring anywhere at that moment. But here's the catch. The frequency of the gravitational waves depends on the mass of the black holes. Stellar mass black hole mergers produce high-frequency waves, hundreds of hertz, that ground-based detectors like LIGO can catch. Supermassive black hole mergers, with their enormous masses and slower orbital periods, produce low-frequency waves, millihertz to microhertz range. These frequencies are far too low for ground-based detectors, which are limited by seismic noise and Earth's vibrations. To detect supermassive black hole mergers, you need space-based observatories. Enter LISA, the Laser Interferometer Space Antenna. LISA is a planned ESA mission, scheduled to launch in the 2030s, consisting of 3 spacecraft flying in a triangular formation millions of kilometers apart. Lasers bounce between the spacecraft, measuring tiny changes in distance caused by passing gravitational waves. LISA will be sensitive to low-frequency waves, making it perfect for detecting supermassive black hole mergers like a hypothetical TON 618 collision. Historians still argue about how common supermassive black hole mergers are. Galaxy mergers are well documented. Galaxies collide and merge regularly, especially in the early universe. When 2 galaxies merge, their central black holes should eventually spiral together. But this process takes time. The black holes initially orbit each other at large distances, slowly losing energy through gravitational interactions with surrounding stars, a process called dynamical friction. This can take millions of years. Once the black holes get closer, within a light year or so, dynamical friction becomes inefficient, and the black holes need another mechanism to lose energy and spiral inward. This is called the final parsec problem, and it's not fully solved. Some researchers think interactions with a circumbinary accretion disk, gas orbiting both black holes, can provide the necessary torque. Others invoke 3-body interactions with passing stars. Either way, eventually the black holes get close enough that gravitational wave emission takes over, and the merger becomes inevitable. Here's your quirky fact. When 2 supermassive black holes merge, the final plunge happens fast. Once they're within a few Schwarzschild radii of each other, gravitational waves carry away energy so efficiently that the merger completes in minutes or hours. The black holes spiral inward at increasing speed, whipping around each other multiple times per second, despite each weighing billions of solar masses, then collide and coalesce into a single larger black hole. The space-time around them rings like a struck bell, emitting gravitational waves that propagate outward at the speed of light. For TON 618, a merger would be spectacularly energetic. If it collided with another black hole of comparable mass, say 50 billion solar masses, the resulting gravitational wave signal would be detectable across most of the observable universe. LISA could catch it easily, even from billions of light years away. The waveform would encode information about the masses, spins, and orbital dynamics of the merging black holes, providing a detailed snapshot of the event. And there's a visual counterpart. Merging supermassive black holes are often surrounded by gas and stars. As the black holes spiral together, they stir up the accretion disk, potentially triggering a bright electromagnetic flare, a burst of X-rays, ultraviolet light, and visible emission. Catching both the gravitational wave signal and the electromagnetic counterpart would be the holy grail of multi-messenger astronomy, allowing us to study the merger from multiple angles. But let's be clear, we don't know if TON 618 has merged since we last saw it. The light we observe left 10.8 billion years ago. In the intervening time, TON 618 could have merged with another black hole, remained dormant, or even been kicked out of its galaxy by gravitational recoil, a phenomenon where asymmetric gravitational wave emission imparts a kick to the merged black hole, potentially ejecting it from the galactic center. These kicks can reach speeds of thousands of kilometers per second, enough to fling even a supermassive black hole into intergalactic space. Detecting a TON 618 merger would also tell us about black hole demographics. How common are ultramassive black holes? How often do they merge? Do they grow primarily through accretion or mergers? These are open questions, and gravitational wave astronomy will help answer them. LISA will survey the universe for supermassive black hole mergers, building a census of these events and revealing the hidden dynamics of galactic evolution. There's also the possibility of catching TON 618's past mergers. If TON 618 grew through multiple mergers over its lifetime, each merger would have emitted gravitational waves. those waves are still travelling through space, spreading outward at light speed. Depending on when the mergers happened and where we are relative to TON 618, some of those gravitational waves might reach Earth in the coming decades or centuries, detectable by future observatories. We could in principle reconstruct TON 618's merger history by catching these ancient signals. You close your eyes, imagining Lisa floating in space, its 3 spacecraft tracing a silent triangle, lasers flickering between them, and somewhere, billions of light years away, 2 black holes spiral together, warping space-time so violently that the ripples propagate across the cosmos. Lisa catches the signal, a faint oscillation in the fabric of reality, and astronomers decode it, reading the story of 2 monsters becoming one. It's astrophysics as archaeology, digging through gravitational wave data to unearth the universe's violent past. Let's step back from the technical details and ask the bigger question. What does TON 618 mean? Not in terms of physics or cosmology, but existentially. What does it say about our place in the universe, about scale, about the limits of human comprehension? Because sometimes the most interesting thing about an object isn't what it is, but what it makes you feel. TON 618 is a monument to scale. It's so large, so massive, so luminous that it defies everyday experience. You can't compare it to anything familiar. Saying it's 66 billion times the mass of the Sun is mathematically accurate but emotionally meaningless. Your brain has no anchor for that number. It's not that you can't imagine it, it's that imagination itself breaks down. You're left with abstraction, a symbol on a page that represents something unimaginable, and that's humbling. We spend most of our lives convinced that we matter, that our concerns are significant, that the dramas of human existence are cosmically relevant. Then you look at TON 618, a single object, one black hole among billions, sitting in a galaxy among trillions, and you realise how microscopically tiny our corner of reality is. Earth is a speck, the Sun is a speck, the Milky Way is a speck, and TON 618 is just one citizen of a universe so vast that even it is negligible in the grand scheme. Historians still argue about whether this perspective is depressing or liberating. Some find cosmic insignificance crushing. If we're so small, do our lives matter? But there's another way to see it. If we're so small, then our mistakes, our anxieties, our petty conflicts, they're not as important as we think. The universe doesn't care whether you embarrassed yourself at work or whether your neighbour has a nicer car. TON 618 is out there, blazing away, indifferent to your existence, and there's a strange comfort in that indifference. Let's talk about the limits of knowledge. TON 618 is observable, but barely. We can measure its mass, estimate its distance, model its accretion disk, but we're seeing it as it was 10.8 billion years ago. We have no idea what it looks like now, in its own present. It might be dormant. It might have merged with another black hole. It might have been ejected from its galaxy. We'll never know, because the light showing us its current state won't arrive for another 10.8 billion years, long after the Sun has died and Earth is gone. This introduces a weird temporal disconnect. TON 618 exists, but in a sense, it's a ghost. The object we're studying is the past, a historical artifact. The real TON 618, the one existing right now in its own timeline, is forever hidden from us. We're looking at fossils, snapshots frozen in light, and we're reconstructing a narrative from incomplete data. It's history, not observation, and that changes the nature of what we're doing. Here's your quirky reflection. Every time you look at the night sky, you're looking into the past. The light from stars takes years, centuries, or millennia to reach your eyes. You're seeing those stars not as they are, but as they were. The universe you observe is a patchwork of different moments stitched together by the speed of light. TON 618 is just the extreme version, so far away that the past you're seeing is cosmologically ancient. And yet, despite being so distant and so alien, TON 618 is made of the same stuff as you. The atoms in your body, carbon, oxygen, nitrogen, were forged in stars and scattered into space by supernovae. The gas and dust that TON 618 is consuming were also made in stars. The laws of physics governing TON 618's event horizon are the same laws that govern your heartbeat. There's a continuity, a connection, however tenuous. You and TON 618 are both part of the same universe, playing by the same rules, separated by distance and scale, but fundamentally related. Let's also consider the aesthetic angle. TON 618 is beautiful in an abstract sense. Not beautiful like a sunset or a piece of music, but beautiful in its extremity, its defiance of normalcy. It's the universe pushing physics to its limits, creating something so extreme that it borders on absurdity. There's elegance in the equations that describe it, a kind of mathematical poetry in how mass-warped space-time and light bends around event horizons. Scientists talk about elegant solutions and beautiful theories, and TON 618 is a manifestation of that beauty. Nature showing off, demonstrating what's possible within the rules of relativity and thermodynamics. Philosophically, TON 618 also raises questions about existence itself. What does it mean for something to exist if no one can ever visit it, touch it, or interact with it? TON 618 is real, but it's so far away and so hostile that it might as well be fictional. Its reality is mediated entirely through instruments and mathematics. You accept its existence based on spectra, redshifts, and models, not because you've seen it with your own eyes. In that sense, TON 618 is as much a conceptual entity as a physical one, a node in our map of the universe rather than a tangible object. And that brings us to the final point: wonder. TON 618 exists because the universe is capable of producing it. Somewhere in the equations governing gravity, quantum mechanics, and cosmology, there's room for 66 billion solar mass black holes blazing at the heart of galaxies. The universe is not just large, it's creative, generating structures and phenomena that exceed our wildest expectations. TON 618 is a reminder that reality is stranger and more varied than fiction, that the cosmos is full of surprises, and that no matter how much we learn, there will always be something new, something weirder, something more extreme waiting to be discovered. You nestle into the pillow, letting that thought settle. TON 618 isn't just a black hole, it's a symbol, a testament to the universe's capacity for extremes. It's a mirror reflecting our own smallness and a window into possibilities we're only beginning to understand. And it's out there, somewhere, blazing or dormant, existing or evolved, forever beyond reach, but never beyond imagination. So where does that leave us with TON 618? After all these numbers, all these comparisons, all these thought experiments about tidal forces and time dilation and gravitational waves, what's the takeaway? What's the legacy of this cosmic behemoth, and why does it matter that we've studied it? TON 618 has become a benchmark in astrophysics. When researchers model supermassive black hole growth, they use objects like TON 618 as test cases. When theorists simulate galaxy evolution, they need to account for the existence of 66 billion solar mass monsters in the early universe. TON 618 isn't just an interesting curiosity, it's a constraint, a data point that any comprehensive theory of cosmology must explain. If your model can't produce TON 618, your model is incomplete. It's also pushed observational astronomy to its limits. Studying TON 618 requires coordinating telescopes across multiple wavelengths, developing sophisticated data analysis techniques, and building instruments sensitive enough to detect faint signals from billions of light years away. Every observation of TON 618 is a technical achievement, a demonstration of how far our technology has advanced. 50 years ago, TON 618 was a smudge on a photographic plate. Today, we can measure its mass, estimate its accretion rate, and model its environment. 50 years from now, who knows what we'll be able to do? But there are still mysteries. We don't fully understand how TON 618 grew so large so quickly. We don't know what its host galaxy looks like in detail. We don't know whether it's still active or has gone dormant in the billions of years since the light we see left. We don't know if it's merged with other black holes or been ejected from its galaxy. Every answer raises new questions, and that's exactly how science should work. Historians still argue about whether TON 618 will remain the most massive black hole we know, or whether future surveys will discover even larger ones. As telescopes improve and surveys cover more of the sky, we might find black holes pushing 100 billion solar masses or more. TON 618 might be dethroned, relegated to one of the most massive, rather than the most massive. But even if that happens, it will remain historically significant, the black hole that forced us to rethink our assumptions about the limits of growth in the early universe. Here's your final quirky fact. TON 618's name is completely unremarkable. TON stands for Tonantzintler Observatory, and 618 just means it was the 618th object catalogued in that particular survey. There's no poetry, no grandeur, just a bureaucratic label assigned decades before anyone realised what they were looking at. It's a reminder that discovery is often mundane, incremental, and accidental. The universe doesn't announce its wonders with fanfare. It just sits there, waiting for someone to point a telescope in the right direction and take a closer look. Let's talk about ongoing research. TON 618 is still being observed, studied, and modelled. New instruments like the James Webb Space Telescope will provide infrared observations that might reveal details about the host galaxy. Future X-ray missions could study the accretion disk's high-energy emission more precisely. LISA, once launched, might detect gravitational waves from TON 618 if it merges with another black hole in the coming decades, relative to our observation timeline, not its own. Every new data set adds a piece to the puzzle. There's also theoretical work. Researchers run simulations of black hole growth, testing different scenarios for how TON 618 might have formed. They model accretion disks, jets, and quasar feedback to understand the physical processes at work. They use TON 618 as a case study to refine their understanding of extreme gravity, high-energy astrophysics, and cosmological evolution. It's a living laboratory, even if the living part is 10.8 billion years out of date. And then there's the educational value. TON 618 captures imaginations. It's the kind of object that makes people stop and think, that inspires curiosity and wonder. Students learn about it in astronomy classes. Science communicators use it to illustrate cosmic scale. It's a gateway to deeper questions about the universe, a hook that draws people into the broader story of cosmology and physics. In that sense, TON 618's legacy isn't just scientific, it's cultural, a shared reference point in humanity's ongoing attempt to understand the cosmos. Let's end with perspective. Right now, as you lie here, drifting towards sleep, TON 618 is out there. Or rather, it was out there, 10.8 billion years ago. The light that left it back then is still travelling, spreading outward in an ever-expanding sphere. Some of that light has reached Earth, captured by our telescopes. Most of it has passed us by, continuing into the depths of space, carrying the story of TON 618 to regions of the universe we'll never see. And in TON 618's present, whatever that looks like now, the black hole continues its existence, governed by the same laws of physics that govern you. It might be quiet, dormant, a relic of a more violent era. Or it might still be active, blazing away, feeding and growing. Either way, it's real, it's out there, and it's a testament to the universe's capacity to create things beyond our comprehension. You take a slow breath, feeling the weight of the blanket, the softness of the pillow. TON 618 is impossibly distant, impossibly massive, impossibly bright, but it's part of the same universe you inhabit, the same reality you navigate every day. And knowing it exists, knowing that the cosmos can produce something so extreme, so alien, so magnificent, somehow makes your own small existence feel a little more connected to the grand tapestry of reality. The universe is vast, it's strange, it's full of monsters like Ton 618, burning and spinning and warping space-time in ways that defy imagination. But it's also your home, the only universe you've got. And tonight, as you drift off, you carry with you the knowledge of something extraordinary, a story written in light and gravity, and the patient observations of astronomers who pointed their instruments at a distant speck and discovered one of the most powerful objects in existence. TON 618, a catalogue number, a black hole, a mystery, a marvel. The numbers fade now, gently dissolving like sugar in warm water. Ton 618 becomes less a collection of facts and more a presence, a distant whisper in the cosmic dark, something you've touched briefly with your mind before letting it drift back into the depths from which it came. There's no urgency here, no need to remember every detail. The black hole will continue its journey, past, present, or future, regardless of whether you recall its exact mass or luminosity. What remains is simpler. The awareness that such things exist, that the universe is vast enough and old enough and strange enough to create wonders beyond counting. You're warm now, settled into the familiar comfort of your own small world. The pillow cradles your head. The blanket holds the heat of your body close. Outside, perhaps stars shine in their quiet way, and among them, invisible, unreachable, but undeniably real, Ton 618 blazes or rests, patient and eternal, a monument to scale and time. Let the thoughts drift. Let the mental images blur and soften. The event horizon, the accretion disk, the jets lancing through intergalactic space. They all recede now, fading into the background hum of sleep. You've travelled far tonight, across billions of light years and billions of years, and now it's time to return, to let the cosmos spin on without you for a few hours. Somewhere, impossibly distant, a black hole bends light around itself, and here, impossibly close, you breathe slowly, evenly, sinking into the gentle darkness of rest. Both are real. Both are part of the same universe. And that's enough. The journey is over. The story is told. Close your eyes. Let go. Sweet dreams.